Imagine a massive solid steel pipe, right? And it's carrying liquefied natural gas.
Yeah, which is incredibly volatile.
Exactly. The fluid inside is flowing at like minus 162 degrees Celsius.
It's almost hard to fathom that kind of cold.
It really is. I mean, if an unprotected worker accidentally brushes their arm against that steel, it's just an instant catastrophic cold burn. Tissue damage is immediate.
Oh, absolutely. And it's not just the danger to people either.
Right. If the ambient humid air around the plant simply touches that freezing pipe, massive blocks of solid ice will just, form out of thin air.
Yeah, and eventually that adds so much weight that it can literally tear the entire mechanical infrastructure apart.
Which is terrifying. So today we are looking at the exact legal and scientific blueprint for the invisible armor that prevents this from happening. Welcome to the deep dive.
Thanks for having me. And, this topic, it is the absolute definition of an engineering tightrope walk, without a very specific kind of highly engineered protection. These extreme industrial facilities, whether they are LNG plants, chemical refineries, or massive power stations, they simply cannot exist in the natural environment.
And that brings us to our mission for this deep dive. We've got our hands on the blueprint for that exact protection. It's a highly technical document called a FIDIC Red Book Scope of Work for Cold Insulation Works.
Which is quite a mouthful.
It really is. Now, you might be wondering why we are dedicating our time to an industrial insulation contract, but as we comb through these pages, you realize this isn't just about wrapping pipes to keep them cold.
Not at all.
This document is a masterclass in how massive engineering projects control absolute thermodynamic chaos down to the exact millimeter.
Yeah.
And, while shifting massive financial liability.
Right. And to set the scene for you, we first have to understand what a FIDIC Red Book actually is.
Yeah, let's unpack that. What does FDI even stand for?
So FIDI stands for the International Federation of Consulting Engineers. They are essentially the gold standard for global construction law.
Okay, got it.
When someone builds a multi-billion-dollar infrastructure project, they don't draft a contract from scratch. They use a FIDI template.
That makes sense. Why reinvent the wheel?
Exactly. And the Red Book specifically is the version used when the person buying the facility does all the design, and the contractor just builds it according to those strict rules.
So they just follow the instructions.
Right. We are exploring the fascinating intersection where extreme thermodynamics meets rigorous safety protocols, all governed by this meticulous construction law.
Okay, let's unpack this. So the Red Book is the ultimate instruction manual. And when I was looking through the materials section, the sheer scale of this manual is what really jumped out at me.
The scale is massive.
We are talking about protecting everything from tiny, quarter-inch instrument pipes all the way up to 44-inch main lines. And the insulation thickness ranges from just 25 millimeters to a massive 400 millimeters. I mean, my first thought was you obviously can't use the pink fiberglass stuff you put in an attic for this.
No. Not even close. The contract mandates highly specialized materials for very specific extreme environments.
Like what?
For instance, the cornerstone material mentioned for cryogenic, meaning extremely cold applications, is cellular glass, often referred to in the industry as foamglas.
I saw that term, foamglas, but I struggled to picture it, to be honest. Is it like glass that acts like a sponge?
Not quite. Think of it more like millions of microscopic, completely sealed glass bubbles fused together into a rigid block.
Oh, weird. Okay.
Yeah, and because it is pure glass and every single cell is closed, it is totally impermeable to liquid water and, more importantly, water vapor. Moisture simply cannot pass through it.
That makes total sense for pipes, but the text also talks about insulating massive building-sized LNG storage tanks.
Right.
I mean, you can't just wrap a giant dome in rigid glass blocks easily. That sounds like a nightmare.
Well, you'd be surprised they actually do use glass blocks for the base of the tanks because it can support immense weight.
Oh, I hadn't thought of that.
But for the walls, the annular space between the inner freezing tank and the outer concrete shell, the contract specifies perlite loose fill insulation.
Perlite, that's the stuff in potting soil, right?
Exactly. Perlite is a naturally occurring volcanic glass. When you heat it rapidly in manufacturing, it pops like popcorn, expanding up to 20 times its original volume.
Wait, really? It pops?
Yeah, literally. So they literally pour thousands of tons of this incredibly lightweight pops volcanic glass into the hollow walls of the tank to act as the thermal barrier.
That is wild. So they are essentially pouring specialized volcanic sand into the walls of a gigantic cooler.
That's a great way to put it.
But wait, what happens when space is an issue? A facility like this must have areas where pipes are stacked so closely together you couldn't possibly fit 400 millimeters of thick glass blocks around them.
That is precisely where the document introduces aerogel blankets.
Aerogel.
Yes, aerogel is one of the most fascinating materials on Earth. It was originally heavily utilized by NASA. It's a solid material, but it is composed of up to 99% air.
99% air. How is it even a blanket?
I know, it sounds impossible.
Yeah.
But the microscopic pores inside aerogel are so incredibly small that gas molecules literally do not have enough room to bounce around and collide with each other.
Oh, wow.
It effectively breaks the physical mechanism of heat transfer. So you can use a fraction of the thickness of aerogel to achieve the same thermal resistance as massive blocks of other materials.
Okay, so we have popped volcanic glass, microscopic air-trapping NASA blankets, and blocks of millions of glass bubbles.
Right, the arsenal.
Plus, the text mentions PIR and PUR, polyisocyanurate, and polyurethane rigid foams for less extreme above-ambient cold service.
Right, the standard foams.
With so many different materials and sizes, how does a massive construction site keep thousands of tons of these vastly different materials from ending up in the wrong place?
That organizational nightmare is solved by the WBS, or Work Breakdown Structure Codes.
Okay, I saw those numbers everywhere.
Yeah, the WBS is the accounting DNA of the entire project. The contract forces the contractor to treat different base materials with intense specificity.
Give me an example.
So insulating a standard carbon steel pipe is tracked under WBS 500.
Right.
But if you are insulating a stainless steel 316L pipe, that is an entirely separate ecosystem tracked under WBS 503.
I wanted to ask about that. The text repeats 316L stainless steel constantly. Why not just say stainless steel? What does the 316L actually mean for the contractor?
It's crucial. The 316 refers to an alloy that includes molybdenum, which drastically increases its resistance to harsh, corrosive environments, like, say, a coastal LNG plant exposed to salt water.
Ah, okay. And the L?
The L stands for low carbon. When welders are fusing pipes together, regular stainless steel can suffer from weld decay, where the heat causes it to lose its anti-corrosive properties right at the joint.
That sounds bad.
It is. 316L prevents that. The bureaucracy tracks it separately because if a contractor accidentally wraps a cheaper carbon steel pipe using the insulation rules meant for 316L, the trapped moisture dynamics might cause the carbon steel to rapidly rust and fail.
Here's where it gets really interesting, though. We have the materials, and we have the WBS codes ensuring the right material goes on the right pipe. But there's a sequence requirement in the pre-installation funds that confused me.
Which one?
It mandates that all pressure testing and system tests must be 100% finished and physically signed off before any insulation is applied. If they know the pipe is fully built, why do they have to wait for a pressure test to put the foam on?
Because of the vapor barrier.
The seal.
Exactly. What's fascinating here is that when this insulation goes on, it is coated in specific mastics, metallic tapes, and weatherproof cladding to create a continuous vapor-tight seal.
Right.
If the contractor insulates a massive pipe and then the engineers pump high-pressure water through it for a test and find a tiny leak at a weld, you wouldn't see it.
Oh, because it's covered.
Right. The water would seep into the tiny gaps between the pipe and the insulation, freeze when the plant goes live, and completely destroy the insulation from the inside out.
That makes total sense.
The pipe is effectively entombed, so it has to be flawless before the tomb is sealed.
Entombed. That's a strong word. That brings up the installation standards, which seem bordering on obsessive. The text references ASTM, C450, and C585, which, frankly, sound like droids from Star Wars.
Yeah, they do.
What do those rules actually dictate?
Those are standards set by the American Society for Testing and Materials. C450 and C585 are essentially strict geometric rulebooks.
Geometric, like shapes.
Exactly. They dictate the exact mathematical dimensions and shapes that these rigid blocks of cellular glass or foam must be cut into, so they perfectly hug the curve of a specific pipe diameter.
I see.
If the geometry is off by even a few millimeters, you leave a gap of air. And in extreme cold systems, a gap of air is a death sentence.
Wow. The document also mentions a strict rule about applying multi-layer insulation. It states that joints must always be staggered. I'm assuming that means you can't line up the seams of the inner layer of foam with the seams of the outer layer?
Never. If you stack seams directly on top of each other, you create a through joint. In the industry, they call that a thermal bridge.
Thermal bridge. Meaning heat crosses it.
Precisely. It creates a direct, uninterrupted path for ambient heat to travel right through the insulation and hit the freezing pipe. That bridge causes immediate condensation, ice buildup, and destroys the efficiency of the system.
So staggering them fixes that.
Yeah, staggering the joints forces the heat to take a labyrinthian path, effectively neutralizing it.
Okay, I understand the theory, but I'm looking at a massive physics problem here.
Okay, let's hear it.
If you build a pipe at a normal outdoor temperature, wrap it in 400 millimeters of solid cellular glass, seal it perfectly tight with staggered joints and metallic vapor barriers, what happens when they actually turn the plant on?
The temperature drops.
Drastically. Steel dramatically shrinks when you pump minus 162-degree liquid through it. A long stretch of mainline pipe will physically shrink by inches. Doesn't that movement just rip all those rigid glass blocks to shreds?
It absolutely would, if not for the expansion and contraction systems detailed in the contract.
Oh, so they planned for that.
They have to. The engineers know the steel is going to shrink, so they require the contractor to install engineered weak points, specifically contraction joints or soft packs, at calculated intervals.
What are soft packs?
These are bands of compressible fiberglass or mineral wool inserted between the rigid blocks of glass. When the steel pipe shrinks and pulls the rigid insulation along with it, these soft packs compress, absorbing the movement so the rigid blocks don't crack.
So they essentially build shock absorbers into the insulation.
Precisely. And it's not just the horizontal shrinkage either.
What else?
A 44-inch pipe full of liquid is staggeringly heavy. If you wrap it in insulation and let it rest on a steel support bracket, the sheer weight of the pipe would crush its own insulation against the bracket.
Oh, right, and that destroys the vapor barrier.
Exactly, creating a massive thermal bridge.
So how do they hold the pipe up without crushing the armor?
The contract mandates high-density polyurethane inserts and heavy-duty metal support shields at every single hanger and support bracket.
Okay.
These high-density blocks are integrated seamlessly into the softer pipe insulation, carrying the immense weight of the pipe and transferring it to the steel bracket outside, all without breaking the continuous vapor seal.
I'm seeing a contradiction, though.
How so?
Well, we've established how permanent and sealed this system has to be, entombed, like you said. But an industrial facility isn't a museum piece. It has moving mechanical parts.
That's very true.
I'm looking at the WBS codes for valves, WBS 501, and flanged mechanical joints under WBS 502.
Mm-hmm.
These parts require routine maintenance. A technician has to inspect those bolts eventually.
Mm-hmm.
If they are permanently entombed in cellular glass, mastic sealants, and stainless steel cladding, how do they ever get to the valve?
They fabricate removable insulation.
Removable?
Yeah, for anything requiring routine maintenance, the contractor cannot use that permanent rigid entombment. The Red Book explicitly details the fabrication of bespoke, removable jackets.
So the maintenance crews just unstrap a custom jacket?
That's the idea. The contract specifies these jackets must be made from flexible mineral fiber, or those aerogel blankets we discussed earlier.
Oh, the NASA blankets.
Exactly. And to protect the blankets from tearing, they're enclosed in a stitched stainless steel wire mesh or a heat-resistant fabric cover.
And how does it stay on?
To fasten them, the contractor uses stainless steel lacing wire or, believe it or not, heavy-duty industrial Velcro.
Wait, really? Velcro? It's wild to think about a multi-billion-dollar energy supply chain relying on strategically placed Velcro.
It is pretty funny when you think about it.
But it makes sense. A maintenance tech can unlace the jacket, inspect the flange, and strap it right back on.
And this highlights a critical distinction the contractor must manage. This removable system is the complete opposite of encapsulation, which is WBS 519.
Encapsulation? That sounds permanent.
It is. Encapsulation is the permanent external weather-tight enclosure using approved metal cladding and sealants. You do not easily unwrap WBS 519.
So if you mess up the coat?
Yeah, if a contractor accidentally uses permanent encapsulation on a maintenance valve, the facility owner has to literally destroy the insulation to do a basic inspection.
Which introduces massive liability. Now, up to this point, we've really been talking about thermodynamics and protecting the facility's machinery from the environment.
Right.
But there's an entire section of this Red Book that completely flips that dynamic. We usually think of insulation keeping the cold in, but WBS 518 is intensely focused on protecting the human beings from the extreme temperatures.
Yes, WBS 518 is entirely dedicated to personnel protection, specifically cold burn prevention.
The contract states that for pipe work located within personal access zones, which basically means anywhere a worker could reasonably walk, reach, or fall, the contractor must install rigid PIR or PUR insulation with 316L stainless steel cladding, and it dictates thicknesses purely for human safety. For instance, putting 40 to 90 millimeters of insulation around a pipe solely to ensure the exterior metal is warm enough to safely touch.
Because if we look at the broader health, safety, and environment, or HSE implications, the risks in this environment are profound.
Definitely.
But it's not just the act of freezing pipes that pose a danger. The physical act of installing this insulation is incredibly perilous for the workforce.
That's something I struggle to visualize. We are talking about these blocks of glass and foam like they're a giant Lego set. What is the actual physical risk to the person building it?
Well, first consider the materials. Cutting and shaping cellular glass or mineral fibers generates hazardous dust.
Oh, right. Respiratory issues.
Exactly. Workers face severe respiratory risks if the environment isn't strictly controlled with specialized ventilation and protective equipment.
And they aren't exactly doing this in a comfortable workshop, right?
No. Second, consider the location. You're doing this suspended 100 feet in the air, balancing on scaffolding, exposed to the weather.
Sounds awful.
It's grueling. You are manually handling thick, heavy sheets of stainless steel cladding, trying to precisely mate geometric shapes of glass around a pipe without compressing it or creating a thermal bridge.
So one slip and you drop a sheet of heavy steel on a crew below,
Yep.
or you compromise the vapor barrier of a massive chemical tank.
Which is why the Red Book demands that all operatives hold relevant trade qualifications.
They can't just hire anybody.
No. The site supervisor alone must have a minimum of 5 years of documented experience, specifically on oil, gas, or LNG projects. You cannot pull general construction laborers off the street for this.
Okay, so we have a system where a single unstaggered joint, a skipped vapor barrier, or a misplaced Velcro strap could cause a billion-dollar mechanical failure.
Basically.
Who is actually taking on the legal and financial liability to ensure that doesn't happen? Because frankly, I wouldn't want that job.
The contractor takes the risk, and the Red Book governs exactly how they are held accountable through extreme bureaucratic strictness.
Bureaucracy at its finest.
Truly. A contractor cannot simply win the bid and show up with foamglas. Within 21 days of the contract award, they must submit a project-specific quality plan conforming to ISO 9001.
Oh, wow.
But the real mechanism of control is the inspection and test plan, or the ITP.
I saw the ITP mentioned constantly. It heavily relies on something called hold points. Walk me through what a hold point actually looks like on a site.
A hold point is an absolute non-negotiable pause in construction.
Non-negotiable.
Right. Let's say a contractor has spent 3 days preparing the bare steel surface of a massive tank, applying anti-corrosive coatings. The next step is gluing the first layer of cellular glass.
Makes sense.
If the completion of the coating is designated as a hold point in the ITP, the contractor literally cannot glue a single piece of glass until the employer's engineer physically climbs up the scaffolding, inspects the coating, and signs a piece of paper.
Wait, what if the contractor's falling behind schedule and just decides to keep working? Like they apply the glass over the coating before the inspector arrives.
Then they have violated the Red Book.
What happened?
The engineer will issue a non-conformance report, an NCR. The contractor is legally obligated to tear out all the freshly installed cellular glass, clean the surface, allow the inspection to happen, and then rebuild it. Ouch. And they must do it entirely at their own cost. The employer pays absolutely nothing for rework caused by a skipped hold point.
That is brutal. The financial risk for the contractor is massive, which makes me wonder how the daily billing actually works.
It's very specific.
The contract uses a unit rate schedule priced in euros, and it describes those rates as being fully composite. Why use that specific billing structure?
It is entirely about shifting the financial risk of unforeseen complexities from the employer to the contractor.
Okay.
Fully composite means a single line item rate, say 100 euros per linear meter of pipe, must include literally everything.
Everything.
Everything. That one number has to cover the raw material, the labor to fabricate it, the scaffolding required to reach the pipe, the respirators the workers wear, the sealants, and the contractor's profit margin.
So if the contractor realizes halfway through the job that they need to rent more expensive scaffolding to reach a tricky pipe, they can't send a bill for it.
No, they absolutely cannot. The payment rules are fiercely specific. Pipes are paid strictly by the linear meter. Valves are a flat rate per item.
No wiggle room.
None. And there's a crucial clause stating that no extra payment is given for cutting or fitting insulation around complicated structural obstructions.
Oh, wow.
If a worker has to spend 4 extra hours carefully carving a piece of rigid foam to perfectly fit around a cluster of steel supports, the contractor eats that labor cost.
That's tough.
They're expected to have factored the physical reality of the facility into their initial composite rate. It stops endless change orders and budget overruns.
So what does this all mean for us? When we zoom out from the WBS codes, the hold points, and the cellular glass, we see that a dry, highly technical 88-page FEI key contract is actually a survival guide.
That's exactly what it is.
It's an instruction manual that ensures volatile natural gas flowing at minus 162 degrees Celsius remains perfectly stable. It ensures that a worker hundreds of feet in the air doesn't suffer catastrophic cold burns just from doing their job. And it is a ruthless financial framework guaranteeing that every single millimeter of material and every hour of hazardous labor is accounted for and paid for without bankrupting the project.
It completely reframes how you look at the industrial infrastructure around us.
It really does.
The next time you see a refinery, a chemical plant, or an LNG facility, you won't just see imposing steel structures. You'll know that the steel is incredibly vulnerable. And the true marvel is the millions of euros worth of meticulously documented, heavily engineered armor wrapped around it.
And here's a final thought for you to ponder long after we wrap up today's deep dive. Consider the extreme engineering we've explored. The vapor barriers, the microtropic air trapping aerogels, and the rigid layered encapsulation used to control catastrophic temperature shifts. These exact same thermodynamic principles and material sciences aren't just keeping global energy supply chains running here on Earth. They are the foundational blueprints that aerospace engineers are studying right now to design the first permanent, pressurized human habitats for the frozen, incredibly hostile surface of Mars.
That is just incredible to think about.
It is. The extreme industrial engineering we rely on today is quite literally the baseline for human survival tomorrow. Thanks for joining us on this deep dive.
If you're interested in the templates, please visit our shop. The link is in the description.
Thanks for watching. Please subscribe and see next time.